everyone. Thank you very much for joining us today for the AIAA Los Angeles Las Vegas section e-town hall meeting on December 5th, 2020. So we have very exciting topics and speakers today. So before that, we'll show some logistics. This is our tentative schedule because the second speaker just informed us that her talk is going to be a little bit shorter. So we'll move the third talk 30 minutes earlier, around 12:30. That's the only change. But it can be a little bit flexible. And I apologize that our section chair, Dr. Chandrasekhar Sawani, he is not here right now because he has been busy recently. So he asked me to welcome everyone if he cannot show up. If he show up later, we'll ask him to say a few words to everybody. So if anything happened to the Zoom session, then please keep trying to reconnect. It should be, if that happened, everything should be reconnected very quickly. So keep trying. We welcome volunteers. So if you are interested, please contact me or send an email to our session chair with a Gmail listed above. And we have also further events. You can look at aiaa-lalv.org/events. AIAA also have membership program, aiaa.org/membership. So please take a look. During the presentation, please try to type your question in the Q&A box. You can type in the chat, but the speaker might be distracted, didn't know where to find your question, so you can type in Q&A. More toward the end of the presentation, you can raise your hand and you will get unmuted. You are welcome to interact with the speaker at the end. But during the process, it's better to use Q&A. So if your internet limited speed is limited, you can try to use a dial-in, but assume it should be okay, for your internet bandwidth. Just a few words about Southern California. As you all know, Southern California is blessed with, aerospace activities. Individuals and organizations. We have people working on things like James Webb Space Telescope, satellites, astrophysics study, and defense, Super Hornet, Growler, F-35, and we have people doing very exciting solar system exploration like Mars Insight, Mars 2020, Perseverance, JPL. They were company expert doing planetary defense, like our third talk today, and also the space debris mitigation. We have SpaceX launching so many satellites, and also people doing space tourism, like Virgin Galactic, SpaceX, and we have very exciting company joining NASA doing SLS design and the test, and we have students doing great job for aviation and rocketry projects. All those great activity cannot be done without the dedication of our members, with the leadership from Dr. Jeffrey Purcell, advisor, Marsha Aerospace Corporation, and Mr. Bob Brand from Boeing, Defense Space Security, and also other council members. So it's highly appreciated. Well, all volunteers. Once you join AIAA, and you can immediately join the Engage website and chat with other AIAA member, aerospace experts, and worldwide and nationally. So it's a great feature for you. It's called Engage. So we also doing, the regular Saturday or other events to keep people engaged, networking together, have fun, and see what's going on, and see what other people are doing. So these are the upcoming events. So there are a lot of benefits joining the professional societies that include events and resources for STEM outreach. And as you know, AIAA is a very, it's a national and international organization with headquarters in Reston, Virginia. Website aiaa.org is a very, distinguished organization. It was merged from two organizations, one founded by Robert Goddard and the other one founded by the Wright brothers. The merge took place around 1950s or 62, I forgot. So it's a very long history, very reputable organization. So all kinds of resources we publish, We provide resources for education and career, a networking industry guide, and a different level of membership. The educator membership is free, and the student has a great discount, and we have other type of membership. So some context, apologize. That's when the e-membership has the program has stopped, so it's no longer valid. We should have removed it. So our first speaker is our great pleasure and honor is Mr. Dale Tutt. He's the Vice President, Aerospace Defense Industry in Siemens Digital Industry Software, DISW. This is growing importance for and attention to this digitalization in aerospace. Dale is the Vice President of, in this division in Siemens. He is responsible for defining overall aerospace and defense industry strategy for Siemens digital industry software, driving specific industry requirements into software products and solutions, and leading the definition of industry-specific market solution for aerospace and defense customers. Dale has over 30 years of experience in engineering, design, development, and program leadership within the aerospace industry. Prior to joining Siemens, Dale worked at the Spaceship Company, a sister company to Virgin Galactic, as the Vice President of Engineering and Vice President of Program Management, where he led the development and the flight test of vehicles for commercial space tourism. While at the Spaceship Company, he led the team on a successful flight test to space in December 2018. We actually had the astronaut last year, to speak with us. So this is ultra exciting, which Dale can share with us in the future. So prior to working at the Spaceship Company, Dale spent 18 years at Cessna Aircraft and Textron Aviation in program and project management, systems engineering and integration, advanced design, autopilot integration, simulation development, and other engineering roles. In one of his most recent roles at Cessna, he was the chief engineer and program director of the Scorpion jet program, where he led the dynamic cross-functional engineering, supply chain, and manufacturing team to design, build, and fly the Scorpion jet prototype from design concept to first flight in 23 months. That's amazing. And approximate 50% reduction in cost and schedule compared to similar program. That's just amazing. And just mention that there's a design, build, and fly. That's exactly the same title of the AIAA student program. That's called the DBF. It's exactly the same title. It's so important. Before leaving Textron Aviation, he was the engineering director for the Textron Aviation Defense Programs, leading the engineering teams for the Scorpion Jet, T6, Texan II trainer, and the 86 light attack aircraft. Before joining Cessna, Dale worked as an engineer at Bombardier Learjet on the Lear 45 program and the General Dynamics Space System Division on the Atlas 1, 2, and 3AS programs. Dale has a bachelor's science degree in mechanical engineering from University of Nebraska-Lincoln and the MBA from Wichita State University with a concentration in finance. It's just an amazing career. So it's our great pleasure and honor to welcome Mr. Dale Tutt. Thank you, Dale.
All right. Well, thank you, Ken. I appreciate the introduction, and I'm very pleased to be here today with all of you. And I'll share my screen here. And are you able to see my screen okay?
Yes, perfect.
Okay, excellent. All right. Well, thank you, everybody. Today, I'm going to talk a little bit about really the future of aerospace and defense and the need for digital transformation within the industry and what some of our customers are doing to accelerate how they're developing new products. So should have some fun today. So let's see. There we go. So, it's about innovation. And if you, I don't know, 2-3 years ago, there was a study that, noted that about 80% of CEOs listed driving innovation as one of their main strategic priorities. And yet the majority of them admitted that they really didn't have a plan for how to drive innovation. So a bit of a conundrum. You want more innovation in your company, but you don't really know how to drive it and how to get more innovation. And so a lot of companies are using digital transformation now, and that's a lot of what we'll talk about and how it can help with driving innovation. To me, this is, this is probably one of the most exciting times in my career. You forget about some of the stuff around the pandemic, but and some of the challenges that that's brought about. But when you think about the amount of companies that are innovating, it almost harkens back to like the 1920s when the Wright brothers flew in the 1903, and then by the 20s you had hundreds of startups. Everyone is building airplanes. There was like the air races, and there were things that were driving innovation. And we're seeing that again today, and that's what's exciting. You have innovation, electric propulsion, with Bio Aerospace and what they're doing on the on their e-flyer, and you're seeing electric propulsion with a number of different companies. You're seeing this in urban air mobility where there's literally 100, 200 companies that are developing, and it's big companies like Bell Helicopter and Airbus, but it's also a lot of small startups. And it's guys with a great idea, and they want to go out and they want to do something different, and they want to help transform the world. It's in supersonic flight. You have startups now competing in the space where there's really been a void since the Concorde retired. And even in space, and we talked a little bit about SpaceX here, but with even companies like Rocket Lab, that small startups, Virgin Galactic, where I was at, Virgin Orbit, these companies they want to change the world for good, and we're in an amazing time. When you think about the defense side, it's an interesting time as well, and the changes that are being driven in the acquisition processes and the development of new products for defense. I think if you look at what the Air Force and the Navy are doing with respect to the next generation fighters, you think about the UK Tempest program that's being led by BAE, and these companies are wanting to get more capability. They want it to be more flexible, more upgradable. They want to be able to have 6th generation fighter capability at half the price of 5th generation fighters and developed in half the schedule. And it's transformational in order to be able to do that. And we're seeing this early emphasis on manufacturing technology and product support, and as much emphasis on that as you're seeing on the development of new just the new technology. So the digital enterprise is key to being able to get to achieve these goals, and we'll talk about some of that as we go through this today. And interestingly enough, when you think about digital transformation of defense and what Dr. Will Roper is doing within the Air Force, and he recently on the left here released the new, I guess the new plan is a play on the Matrix, so about taking the red pill and really adopting that and embracing that digital transformation. And he unveiled the e-aircraft, where you aviate in the digital space before you actually start building a prototype, and you actually start looking at the airplane and flying it before you build it. And the Boeing T-7A was the first aircraft to be designated with this e-aircraft designation. And so, so this is, again, it's an indication of how digital transformation is being used to drive changes into the industry. So all companies, big and small, to really be able to survive and thrive in this digital era, really need to be, they need to become digital enterprises. They need to think about how they're conducting all their business. And it's not just about going out and buying some new tools, but it's about how their business processes are set up to enable those tools. And it's about the culture change that has to occur within a company and the training. And it's always about the people and how the people adopt the new technology. And when you take this, this view of people, tools, and processes, that's when companies really start to see big transformational results. And so we'll talk about a lot of that today as we go through this. So I always have a little bit of fun. We went, I think I first started going to paperless systems probably in the mid 90s or early 90s. And that was the watchword. And yet I feel like I generate more paper than ever today. And when you think about, you look at this, these two examples of these documents, what's the difference? You have, the document that's spec that's on the left and the spec that's on the right. Well, really, one was created with a typewriter, and one was changed with the word was created with a word processor. But there's really no difference. All they did was change the tool, the medium that was used to create the document, but they didn't actually change their processes or how they conducted business alongside with this. And so they're getting the same result. They create this digital version, they send it to a supplier, a potential supplier, or even a customer if it's an RFP, or sorry, if it's a proposal, and then they kind of go through the standard processes of reviewing documents and then sending information back. But it's not really being done in a model-based way. They're being done in a digital enterprise. And we always joke, the real bad news about the word processor is now you can attach it to an email and you can inadvertently send it to anyone in the world. So it also adds a different level of complexity. So this is highlighting the need for a different approach to digital transformation. And when we talk about digitalization and the business transformation that comes along with it, we think about this spectrum. So I always tell everyone the twin is the what, it's what you're designing. The thread is the connectivity or the context, the how you're going to do it. And we're going to talk a lot more about that as we go through this. But, in the beginning, when people started adopting these new tools, like computer-aided design, it was really just digitizing. So instead of creating 2D drawings on drafting boards, you were creating 2D drawings on the computer. Companies then started applying the twin, the more of the concepts around the twin, the simulation, the models, and 3D CAD models utilizing geometry. And it certainly raised the efficiency of how these models and simulations were done. But at the same time, it didn't really, transform the business. You also started seeing a lot of these other business applications being connected together, but again, not really fully. And it's only when you start to see the full connectivity of the twin, this comprehensive digital twin, that's really when you start to see the real transformation that can happen. So it's the combination of the intelligence of the twin with the connectivity of the thread. And we're going to talk about this quite a bit. So you'll hear that theme a couple times. So now I'm just going to show a very short introductory video about digital transformation and how it's affecting some companies, or how it can drive change. And then we'll go into the rest of the presentation.
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Point-to-point urban mobility will be redefined and won't be limited by gridlock. Electrification will provide greener solutions for air and space travel. It's all enabled.
Ken, are you able to hear that?
Yes, I can hear very well.
Okay. I'm sorry, I'll finish. I inadvertently stopped it, so.
By digital threads that turn silo data into connected disciplines and processes. These threads form the neural network of a digital twin, a virtual entity which mirrors the physical world, turning data into insight to continuously design, build, and optimize throughout the product and production lifecycle. Early simulation creates an agile development environment, allowing faster iteration and encouraging design innovation. This means ensuring complete traceability of requirements for complex products through verification across multiple configurations. Digital threads extend model-based product data throughout the supply chain, enabling automated processes that can predict what's next and improve accuracy. Virtual plant commissioning shifts manufacturing concurrently with updated engineering development. Data gathered after delivery and during operations is used for predictive maintenance and fed back into product development to optimize future designs and maximize uptime. Siemens can help you achieve rapid digital transformation, powered by the world's most comprehensive digital twin. There's no need to dream about the future. It's already here. The pace of...
Okay, and sorry about the stopping it inadvertently in the middle there. So anyway, so a lot of topics covered in that video, and some of those topics around simulation and how you can accelerate some of your design activities, as well as some of the manufacturing concepts are really going to be the focus as I talk about the rest of this, through the rest of this presentation. So anyway, so I'm going to step back a little bit. I'm going to talk about the industry, what's going on in the industry, and then we'll move into some of this digital transformation. So we've already talked about all the innovations going on and the different companies that are involved. But what we're looking at when we talk to companies all around the world is, what they're experiencing. They're seeing this pressure to reduce their program cost and schedule. So you have to get to market faster than everyone else. You have to be able to provide that capability at a lower cost to stay competitive. And then if you're a supplier, you're being squeezed by your OEM to provide parts, or by your customer to provide components at a lower cost. So everyone is feeling this pressure and how they manage their production schedules. We're seeing increased program complexity and integration. As you think about the innovation that's going on in the urban air taxis and supersonic and the defense programs, they're highly integrated. They're becoming more and more complex. So across the board, regardless of what segment of the industry you're in, space, airframe, defense electronics, you're seeing more and more complexity. We're also seeing increased electrification of products, and obviously there's the green propulsion, the electric propulsion that we're seeing a lot of companies are trying to adopt. But even companies that are not going to green propulsion are increasingly adopting more electrification, replacing maybe a mechanical system with an electromechanical system to improve the reliability and maintainability of their product. And then finally, globalization. Whether you're talking about your supply chain or your workforce, you have to be able to collaborate with your team around the globe, be it your partners or your own teams. So these trends drive a lot of complexity into the products. And what we're seeing around, with all of the products, with all of the customers, is they're just seeing more and more complexity, whether it's technical complexity or business complexity with how they're integrating with their partners. And so there are some companies that, there are a lot of companies that try to figure out how to minimize this complexity, how to simplify things so they can minimize the risk that's associated with this complexity and do a better job of managing their schedules and their budgets. But we're actually seeing that the companies that are embracing this complexity and using digital transformation to better manage the complexity, but by embracing this complexity, these companies, they're producing higher performing products, they're doing it faster, and they're doing it at less cost. They're actually working within their planned program budgets much more effectively. And so by embracing this complexity, you can actually gain competitive advantage, and be able to move faster than your competitors. So the keys to using complexity as competitive advantage, what our customers are doing, they're using a comprehensive digital twin, this rich, robust understanding of both your product and your production processes and your product support processes, so that you're able to work more efficiently, more effectively. They're using personalized, adaptable, modern solutions. We're deploying more and more configurable solutions, not customized solutions, so that companies can accelerate the deployment of these new technologies and again, be able to go faster and gain some competitive advantage. And then finally, in a flexible, open ecosystem. And to me, this is probably the most important thing you can have. It's a lot of people say they're open, but to be truly open, to be able to link up to all the legacy tools that are out there, to be able to link up to the best products out there that enable companies to adopt the best practices and the best solutions, is vitally important to being able to move fast. And quite frankly, when you have new technology coming online, you also want to be able to implement it as quickly as possible. And you do that much more effectively when you're working within a flexible, open environment. So why is the digital twin important? So a lot of companies, they're using this understanding to get to faster time to market. They're trying to drive their innovation by having a better understanding of their product and being able to look at more variables faster. Being more adaptive in responding to demand changes. So if you're having to change your production rates, you're able to adapt to those more quickly. If you have requirements change from your customer, you understand the impact, you understand how to implement it faster. Being able to extract value from the complex mountain of data that's being generated and collected. So with all these new systems coming online, we're collecting terabytes of data, and you need to be able to make heads or tails out of it. You have to be able to understand what you're doing with that data. And so, this is an opportunity to use better tools and AI to help manage that data and actually understand and get useful information out of that data. To be able to unite your engineering disciplines across the entire life cycle, to be able to drive to these common business goals, to be much more proactive to events that occur during a program, while still trying to optimize both the quality and the productivity of your engineering and manufacturing processes. And then finally, really being able to use and deliver new business models. So what is a digital twin? When we talk about it, and I've got a couple slides on this, but it's a very, first and foremost, it's a precise virtual representation of a physical product or process. And it's used across its life cycle to simulate, predict, and optimize the product and its production system. And it's not just one thing. It's not just a simulation model, but it's made up of a multiple of representations of models. So it might be requirements. It could be your 3D CAD model. It can be the simulation models or the analysis associated with it. It can be your plant simulations. So it's made up of a lot of different representations that really make up the comprehensive digital twin. And it's evolving as you mature your products through the life cycle. When you're starting in concept design, you probably have a different level of maturity and granularity of your, say, your simulation models. And then as you move through the product life cycle, you want to build on that maturity. You want to increase your level of maturity so that you can actually use those same models and have that continuity throughout the entire process. And then finally, the closed loop digital twin really provides for this bidirectional connectivity between both the physical world or the physical asset and the virtual representation, so that you're able to use that data and leverage that data as you go through it. So in practice, what this looks like is, starting on the left here with the product digital twin. Again, this is the virtual representation of the product. It's the 3D CAD geometry. It's the bill of materials. It's the models. The simulation models. It's the requirements. It's all of the information and data required to define your product. As that specification drives into your virtual production, you use your production digital twin, your plant simulations, all of your planning, your manufacturing processes to help define how you're going to build your product. And then you can do virtual commissioning. And we'll talk a little bit more about this later on. But the whole concept with virtual commissioning is before you start building a new plant or building tens of millions of dollars of new tooling or implementing automation, you want to be able to verify that it works. And so you use those simulations to drive into your real automation, your real production automation. And then finally, you develop your product, the as delivered version of your product. So the connectivity, so as you use the twin to move from left to right, to start with your product design and use that to drive all the downstream processes all the way out to the delivery of your product, the feedback's important. So within your production cycle, you're using the feedback from your real production to optimize your production twin. And as you optimize your production twin, now the next time you use that on another program, it's more accurate. You have a better understanding of it, and you're able to take that organic learning and go faster. Same thing with your real product. As you collect data from the field, maybe it's from your flight test program or actually how your assets are being used out in the field, you're able to drive that knowledge back into your product twin and have a better understanding how your products are working, to be able to adapt if you need to make changes, make changes as a result of something in the field. You're able to do it much more effectively because you have a better understanding of what's going on with your product. And again, just like with production, because you now have this organic learning going on, the first time you go through this process, you might save 20% of your time. Next time you go through your process, you save another 20% of your time. And over time, that really starts to add up. And so this is where the value of digitalization as you go through the entire life cycle of the product. So when we look at air mobility, I'm going to use an example. So it's here we are with this with the innovation around air mobility, and you think about how it's changing the way you're going to transport. So I'm going to fly from my home in Detroit to south of France. I'm going to take an air taxi down to. Actually, I guess I'm in France already there, but I'm going to take an air taxi to the airport. I'm going to get on a supersonic airplane and go overseas very quickly. And then I'm going to get on a zero emission regional aircraft and do that last leg in the zero emission. Maybe it's a hydrogen powered aircraft like what Airbus has recently announced that they're starting to do some R&D on. But these are all much different than how we're flying today, how we're using you know, how we're moving about our cities, about the world. And so to achieve this vision, aerospace companies are going to really need to embrace digital transformation and digital enterprise in their engineering, manufacturing, and product support. So what do these companies have in common? You know, so whether you're an air taxi or a supersonic airplane or a regional transporter for that matter, a a space satellite manufacturer, or even a defense aircraft, these companies all do kind of the same processes. They all have some version of a gated development process, and so they start with concept design, and then they go into their multi-domain product design, the mechanical, electrical systems, the structure, the electrical systems. They then need to verify and certify that the product actually meets the requirements and it can go into service. Throughout the process, they need to be able to manage their programs and also manage their supply chain. At some point, they're going to move into building aircraft and then delivering and supporting aircraft. So these processes, as I said, most companies are doing some version of this, whether it's a brand new product or a modification of an existing product. They're going to go through some process that kind of looks like this. So we've developed industry solutions to help organize all of these different products and all these different solutions and help tie them together, to connect them together, to help accelerate some of these process flows. So things like model-based systems engineering, which has a heavy influence in conceptual design, the product design engineering, which actually does a lot of the detailed design and analysis of your product, and then verification. You have processes for program management with your integrated program planning execution, and then supplier collaboration management, in manufacturing, and product support. And so all of these things, when we put these solutions together, it's really focused on program execution excellence and really helping to partner with customers to help them do this. So I don't want to make this, I'm not trying to make this a sales pitch or anything, but these are some of the solutions that customers are using to help accelerate their digital transformation. And these threads, one thing I don't want to imply is these are not serial activities. These activities, they cover the entire product life cycle of the program. They're not just points in time. And these horizontal threads that you see here, these solutions, there's also this vertical interconnectivity of them. So it really is creating a bit of a fabric, if you will, between all of these processes and all these solutions as companies are implementing the full digital enterprise. So, as we said in the video, it's we often hear about the future of aerospace. We hear about the future of the factory of the future. A lot of those solutions are available today. And so those solutions are available to customers today. And it also is setting the foundation for where we're heading in the future. So where is the technology going? Where are companies now looking to go forward? And so, we've organized our solutions within the Accelerator portfolio. Let's see. Okay. So then here's an example. I always like to share an example. I'm very, I'm always watching what companies are doing and how companies are just totally transforming their business. And I talked earlier about, even in the defense world where, countries, defense agencies are wanting to develop products at half the cost of the previous generation of products. And people sometimes are a little bit skeptical, and then I like to highlight this example here, where Boeing, with the Boeing T7, with the TX program, they bid about half of what the Air Force expected, and it's truly transformational. But that's not all. I think when you start to look at how they have developed their digital enterprise, using model-based engineering, and they're getting 75% increases in their first pass quality, and how it's paying off when they get into the manufacturing environment, where they were able to do splices that previously took 24 hours in like 30 minutes. And they're developing their software in half the time. And as they move into their manufacturing, they're seeing significant, I would just say massive improvements in their manufacturing quality and the reductions in their assembly hours. And so these numbers, I just took them from an Aviation Week article, from May of 2019. But it's a great example of what companies are doing. And I've got a few more of those that I'll share as we go through this. So how can you turn this highly integrated, complex products into competitive advantage? As we start to talk about some of these solutions, I'm going to talk about a couple of these solutions now that we were talking about earlier. So thinking about MBSE, really with the goal of MBSC, companies been doing, systems engineering for 20 years, maybe actually longer than I've been doing it for 20 years. The companies are now starting to use this to shorten their time to market, to be able to do a better job of orchestrating their technical program, managing their scope and cost. And so, our focus of, model-based systems engineering when we work with customers is to really optimize their product architecture, to use requirements to drive design, to develop these optimized solutions, to do a better job of interface definition and managing their integrations, whether it's across the different suppliers or whether it's across the just different systems within a company. And then finally, in the future, to be able to enable digital verification and certification, and having the comprehensive digital thread to really be able to drive that. And so when we think about systems engineering, this is a pretty simplified view of systems engineering, but looking at requirements, the allocation requirements as you go from systems to systems into your aircraft or your vehicle, down to systems and components. At the same time, you're concurrently doing that with your safety requirements development. So you're doing your initial system safety processes. You're actually using that to drive requirements into your subsystems and your components. As you move into the gray area, that's the main part of any program, the detailed design that's occurring. This multidisciplinary design, electrical systems, mechanical, software, hardware engineering, structures, and then finally you move into the verification phases, and looking at component verification, subsystem, maybe it's a bench testing, and then into flight testing if it's an airplane. And you're also at the same time verifying your safety requirements. So when you think about these functions around systems engineering, in the concept design phases, a lot of the activities on the left-hand part of this, in the bluer section of this V, is usually kind of more focused in concept and preliminary design type phases. There's multiple iterations in concept design phase to define the requirements, your product architecture, to be able to meet your target program performance. And so this team might be really small. It might be 30, 40 people at this point in time. A little bit easier to manage, but you want to be able to look at hundreds of options. And you want to be able to know that you selected the best architecture possible. As you move into the design and execution phase and the verification phases, really, what you want to be able to have is a clean handoff from the concept definition phase into your detailed design and verification phases. You need to be able to manage interfaces and integration. I mean, think about some of the challenges you hear about, or maybe have experienced yourself, as aircraft suppliers or aircraft manufacturers have brought sections of airplanes together from different suppliers, and they have integration problems. And then you also need to have a complete verification plan, and that really sets the scope of your program and kind of defines the finish line for you. So what companies a lot of the companies that are seeking, that are using digital transformation now, they're really trying to use that product architecture that was developed in the conceptual design phases and really use that to drive the development and execution success. So don't really, they're trying to move away from, tossing it over the wall to, to the next group of people. And then they start over with a new set of tools, but to really have more continuity and more, to transition more smoothly into those execution phases. And so they want to be able to manage, support all the downstream processes. They want to manage and define their interfaces and do a better job of their integration. And then they want to be able to provide design oversight. So as you get into these execution phases, maybe you have 100 suppliers and you have 1,000 engineers working on something. I mean, it can become very difficult, very challenging to manage when the program changes as you go through these different design phases. And so they want to have stronger tools to be able to do this, and they're using this digital thread and the ability to manage this more effectively. So when you think about the different domains that's required to build, say, build a new product, build a new space launcher, you have your product design and engineering domains, you have manufacturing, supply chain management, so all the different functional areas. But kind of through all of it throughout, you have the model-based systems engineering. So as I said earlier, it's starting with requirements in your system modeling, but it's also ending up with some of your verification management and the verification processes. So whether you're verifying at the component level, the subsystem, or the system level, you need to be able to have that continuity. And with the model-based systems engineering, where where it maybe changes from what we were doing previously. You know, if I think about 5 or 6 years ago, you know, when my team's doing systems engineering, they're managing their requirements in one tool, and they're managing all of these different activities in different tools, and there was a lot of manual data translations, and it was quite frankly kind of hard to manage. And so with model based and using digital thread, you're able to have better connectivity and help manage that data much more effectively. And so what you see with model based systems engineering is really this becomes totally intertwined with all these other processes, really, you know, can really help connect them together. And so, you know, with the model-based system, using model-based requirements instead of document-based requirements, and using your system models where you're able to more efficiently share key parameters and key data, and the interconnections, the interfaces with your design tools as you start designing your electrical system or your mechanical systems, to be able to manage that data much more effectively and then move cleanly into verification management. You know, this is the benefit that we're seeing with the model-based piece of the systems enterprise. So moving on, I'm going to talk a little bit about some of the design solutions, especially around simulation and some of the electrical system design. Again, highlighting the connectivity that you can start to achieve as you digitalize your processes. So how can you overcome all these new design challenges and really create new successful new products? And with product design engineering tools and solutions, you're able to accelerate your design using simulation-driven design to really optimize and balance your solutions across all these different domains. And so before you build, you want to be able to do complete virtual testing based on this, using the you know, the comprehensive digital twin to really minimize your risks and reduce your test costs. You want to be able to do an integrated multi-domain optimization. You can't just you can't just focus on one area at the expense of the other areas and have successful products. And then finally, be able to use advanced technology and really using the simulation-driven design and using these tools that are being driven by the way the product architecture was developed to really to go faster, but to also bring in new technologies like additive manufacturing and composite design, and actually be able to integrate those quickly into your design solutions. So I like what he's talked about, you know, as we, you know, think about the challenges. I mean, just kind of, you know, thinking about like these urban air mobility vehicles, you know, that have all these different rotors on it, and they have a lot of electrical systems. They're managing, you know, with their electrical propulsion, they're managing a lot more, you know, the power density, the way the electrons are going around the aircraft, the EMI effects that you might have from that, the thermal management of all this electrical power that has to be managed. To be able to cleanly do an electrical, electronic, and mechanical software integration and bring those together. Also bringing in a lot of automated flight controls. All of these vehicles are wanting to go autonomous. And so to have more, you know, stronger tools and better connectivity from your requirements through all of your simulation electrical design tools to help develop your automated flight controls. And then, you know, companies are having to work through their verification certification processes really by at the same time that they're trying to balance all of these variables and really develop a great end-to-end customer experience or passenger experience that is safe and reliable. So a lot of challenges that companies are dealing with when you think about this, and you could put this chart together for just about any new product that's coming out in the market today, and think about all the different challenges that have to balance. But this is just an example of that. So thinking about simulation, you know, how do you accelerate the design through the simulation? So, you know, when you think about like this air vehicle here, you know, you start with your, you know, all the different aspects you think about. You think about your battery design and what goes into designing the battery, and even the charging and the management systems of the battery, especially with these with the newer chemistry batteries. You know, the simulation of your electric drive, the motor design, and all of the electrical components that go with it. And you develop your system architecture and looking at system level performance, but to be able to look at all these different scenarios. So with the complexity here, to be able to look at a lot of different scenarios quickly and actually evaluate how your product's going to work in the field, even considering how like different tolerances of your parts and your systems. As you go in through your aircraft engineering there at the bottom right, the aerodynamics, the propulsion, the how you're packaging all of the products, your batteries, and all of the other systems on the vehicle so that they can fit reliably. You're managing your software, and then you're doing this, you're being able to optimize all of the attributes here. You're looking at all of these parameters at one time. You can't just focus on batteries. You can't just focus on propulsion. You can't focus on just structure. You have to look at them all at the same time so you can come up with an optimized overall product architecture. So we talk a lot about the virtual integrated aircraft, the flying it before you build it. And I think this is something a lot of companies are doing today already, at least in some areas. And we're starting to see more and more of this develop, and we're starting to see more and more interest in seeing what companies can do to pursue digital certification. So with the virtual integrated aircraft, because you have this richer understanding of your performance, as you go through and you can look at a whole lot of different scenarios quickly. I think the key things that I get out of this is, one is you reduce the risk of a test program. First, you identify problems before you start building your product. And so now you can have confidence that you can go through your test program more successfully, more cleanly, without having, running the risk of design changes that occur, that are kind of the natural occurrence of a program. I mean, I think about some of the programs when we had a test problem, it might take us 3 to 4 months to solve it. That's a pretty huge impact on a lot of these programs. And so the ability to minimize the number of those changes as you go through a program is a significant step forward. And then the other thing about the test program is, because you've now been able to look at the entire, say, flight envelope of your product, instead of spreading all of your test points out across the envelope, whether it's the loads envelope or the flight envelope, because you're able to identify the more critical areas of, say, your flight envelope, you can now test these. You can focus your flight testing in those areas, and you can actually get a much more efficient test program. So, I think that's again, where you're taking risk out of all your test programs and actually just being more efficient. And then one of the things that we're looking at is, how do you accelerate your testing? I think about some of the flight test programs that I've been on, and we fly our vehicle for 2,000 hours, and my guy has always, we always kind of would sit around and think about, like, when we go do a flight test, we test one set of test points. And so we have a dozen test conditions that we need to apply. And we're really only looking at a handful of the parameters at the time, because we're only looking at the data that was really relevant to that particular flight test point. But in reality, you got 1,200 sensors on your airplane. You're collecting data every single flight. But I have to admit that my teams, we never had the time to look at all of the data every flight, and so we would sit there and we'd focus on the test points, and then if there was a problem, then we'd start going back and looking at all that data. And so now with the twin, with the digital twin, and with some of the new data analytic tools, well, we're trying to look at, how do you take and use that data from the entire flight, every single flight test, and use that to continuously update your models using machine learning, AI, and really help advance kind of the state of the art of your test programs. We used to, I would say we used to think that we maybe could cut our flight test programs in half if we could figure out a way to effectively use every single flight test as a data point. And but we never had the manpower and the budget to do that. So, but I think the tools now are stronger, so companies can really start thinking about a different way of doing it. So just again, a little bit more on now. So to build on that virtual integrated aircraft idea, how do you use this digital continuity with your verification using simulation? So as you go through a program, so at the beginning of time, you have these system development models. They're used primarily to develop the system architecture. And then as you flow down, as you continue to mature your product, these eventually become system verification models. And how those models are used as you go through the whole program, these early models might be used with your virtual Ironbirds. And these, again, really trying to ferret out any potential issues that you might have and minimize the number of design changes as you move into your systems integration testing, or your Ironbird rigs, depending on what different companies call them different things. But as you're getting closer to first flight, you're doing these bench testing, and then you need to be able to then use that information as you go into flight testing and certification. And so it's so again, it's how to use the tools, how to use this, have this digital continuity that allows you to use these tools throughout. So let's see. So I do see a quick question there. I might I'll see if I can take that one real quick. So the question is from Gus, and is this is a great design tool. Some companies have adopted proprietary approach to their processes. Can you elaborate on the best practice approach recommended by Siemens? Yes, absolutely. So I think the big thing is and I've actually been in that environment. And a lot of the simulations that we were developing in the early 2000s and on were developed on homegrown systems, and they were quite capable, but they required to be they required a certain level of maintenance. And the reason that we tended to do our homegrown solutions is because the tools out of the box really weren't necessarily configurable enough to really adopt the to just use them out of the box. So we had to customize them, and so we developed our own proprietary solutions. And what we're looking at Siemens as we continue to develop our solutions, what we really want to see is more out of the box solutions. And so the tools now are getting much more sophisticated. There's a lot more capability. There's a more automation, and they're now able to maybe work a little bit more out of the box, and the modeling methods, and there's a lot of sharing that goes on around modeling methods, and that comes back to us as well. And so we try to adopt those industry modeling, the standards for modeling methods as well. So as we continue to develop these processes, the goal here is to actually be able to use these solutions more out of the box. So even though a company itself may have some unique some unique attributes for their design, and they may do a little bit of configuration of the model, the simulation, the solutions are really intended to be a lot more out of the box. And what we're seeing with customers is that they're able to now use these tools, these solutions out of the box, and they compare quite favorably to the in-house tools as well. And so then the benefit becomes that by adopting maybe an out of the box solution, you can reduce your cost because you're not having to maintain your own model. And then as new technology comes in, because a company like Siemens and our competitors, we're working with a whole bunch of different customers, and so we're providing capabilities for customers all around the world that every company has the opportunity to benefit from. And so I think that's what we see a lot as far as being able to use best practices and really driving towards out of the box configurable solutions versus heavily customized or in-house solutions. So. All right, hopefully that answered there. So if not, just send me another question there. So, and if anybody has a question, I'll try to answer them. If I might need to wait till the end on some of those, but we'll go through that. So so another aspect, building on that whole theme of how do you move from system modeling into using your models for verification. One of the things that we're seeing is being adopted is being able to use these simulations for smarter verification strategies. So as you go through this process, and this is a pretty standard practice of, I have requirements, I'm going to do my verification planning, I decide how I'm going to show compliance, whether it's an analysis or a test, or maybe it's just an inspection or a design review. And then I got to collect up my information, do compliance reporting. Where you start with your requirements, you then figure out your verification strategy. Where are we going to use test articles? Are we going to do it with just analysis? You then go in and do your detailed verification planning. You're developing your test requests, your procedures, your test articles, you're building them. And then you start to execute the tests. You collect all this data. In this case, if you're doing it by analysis, you're doing virtual test data. And then if you're doing virtual test data, it's under configuration control. It's linked back to the configuration of your models. It's linked to your design. It's also linked to your requirements. And so now you know that everything's in sync. And it's also linked to your test article. So again, that that the test article is in sync with your design as well as your current state of your analysis. And as you have confidence now that everything is aligned and it's under configuration control, you're now spending less time managing data and making, trying to adapt for changes. And so, I've been in a situation where the design, we completed the testing, and we were, thought we were done, and then all of a sudden we figured out that the design had changed 6 months earlier, and then we had to go back and redo the test. And so by automating some of these processes and simplifying it and having this connectivity, you're able to actually reduce the risk of having these disconnects that happens once you start your test program. And then finally, you do your verification reports. You're correlating your data, you do your reports, and then you're able to take all of that knowledge back and use it on the next program by you reusing some of this knowledge that you've learned, either in the improvements in your digital twin or in just having modules. You have standard tests set up, standard analysis set up, and you're able to start reusing that because it's linked up and you have the context and how it's been managed. And so, just as a quick example, it's of companies that are actually seeing real world success with using these, taking a more simulation driven approach. Over on the MC21 over in Russia, they've been using virtual testing and simulation models, and they've significantly reduced the number of bench tests. And just on their fuel system alone, they managed to remove 25% of the tests. And when you think about a test regime or test program around a fuel system Ironbird, if you can take 25% off of a 6 to 8 month effort, that's a fair amount of time savings. And if you can do that on all of your systems, or at least some amount on all of your systems, you can truly anticipate a reduction in your overall program length. Or maybe more importantly, or just as importantly, you have a cost avoidance, that you don't have an error, you don't find something, you don't discover something that needs to be fixed and causes a design change. And now you're able to have a much better chance of making your program budget and schedule, if not reducing it. So then another area that we're seeing in design, and a lot of activity with the design, and I talked about this in the industry trends, is this increased electrification. And if you think about it, I always kind of tell the joke that when I was working on the Lear 45, I think we had hundreds of engineers working on the program, and we had like, I don't know, 10, and maybe it's more than 10, but we had a very small number of people that were working on the electrical systems, and that was in the early 90s. And nowadays, a program like when I was leading the Scorpion program, I think maybe 25 to 30% of our team were electrical engineers, and so it's really has been a transformation in the makeup and the skill sets that are required to develop new products. But so you're seeing this, and just in this chart here, just in the power demand, how much power is being developed. It's just phenomenal, or amazing, like what's on the Boeing 787. And if you looked at the Airbus 350 and some of those newer products like that, the amount of electrification is, the power demand is huge. And so there's a lot of wire weight, but with that is coming a lot of new requirements like EWIS, the electrical wiring interconnect systems. And so, the regulations and the costs are growing faster than the content. And so, so how do you manage this? I mean, a lot of companies are managing it with, I know some that are managing it with homegrown systems. They're using older tools that they've customized. And in my past lives, we were relying on a lot of Excel spreadsheets and macros, and it just, we're putting a lot of processes and pieces in place to try to manage just the sheer volume of data that we had to go sort out with all of the networks and all the electrical systems. And so, so as you think about these tools, so what are you doing? What are companies trying to do as they go through this process? Earlier, when I showed moving from concept design into product engineering and into verification. So what are these companies trying to do? So starting on the left here, you start with requirements, and then you do your system modeling. And so for an electrical system, electrical and electronic system, you then move into you're developing your system model and your electrical system architecture. So, and this kind of splits into two paths: your software and network architecture, as well as in your logical systems and all the ICDs. And that feeds into your electronic system. So you have your electrical system, and then that's feeding your electronic system, where you're designing all the different boxes and developing your software. And so, you then are moving into, software architecture and developing your network communications and then the software itself. And then with your electrical system itself, you're thinking about the distribution system, and then how does the distribution system drive your harness design, and then how does that drive how you're going to build the harnesses, plus how you're going to support them out in the field. And so you have to be able to manage all this data throughout, and as you go through these processes. So as you're taking these model data from these system models over on the left all the way through to the end to your documentation, how are you driving those engineering flows so that you can actually have the context of a part. Have the context of how the final product at the end matches your system modeling and the requirements up front. So then if you think about a view of like what we're doing with capital, within our electrical systems development tools, we've developed it around those processes, those process flows that, most of our customers are using. And then around that, we've wrapped, this continuous verification and validation. And this has taken all the data, and it's helping to automate some of these processes so that you're not manually doing it. You're not manually translating this data, which, sometimes can cause errors. And it helps with the integration because you're now being able to manage, these as you move through the different steps of the process. And all of this is on top of, your enterprise PLM systems, and you're also interfacing with your mechanical CAD and all your manufacturing processes and all your supply chain processes, and as well as your program management. So so again, like that slide earlier that I showed where we had the horizontal threads, and I mentioned that you have all these vertical interconnections that's really creating a fabric. Think about this as a horizontal thread around electrical system design, but it's also got to integrate with everything else that's on an airplane. It's got to integrate with your mechanical systems, and it's got to integrate with your manufacturing, all your other systems. And so again, this is part of that fabric. And then the nice thing about it is think about this as you're going through the design phases, and how do you also accelerate your product compliance? So as you're going through and using this continuous verification, you're able to continuously verify that the design is compliant. You're not stopping, you're not waiting to the end to check your system. You'll start to see this in real time because you're automating some of these processes, those data translations, as you're moving from one phase of software architecture, network architecture development into your software. And you can also build in constraints, so you can actually verify that, like if you're talking about your electrical wire harnessing, that you can put in those separation constraints that you need, left hand, right hand, top, bottom of your airplane, to be able to show that, as you're developing it, that you've automated some of that checking that can be so painstakingly tedious, that we've been able to automate some of those processes. And this is really this can only be done because you have a digital twin of your product and a digital twin of your electrical system. And so anyways, through this automation and through the continuous verification, the connectivity you get with the digital thread, and the robustness of the understanding of your product with the digital twin, you're now able to automate a lot of these processes and really accelerate them throughout. But I think the main thing is then, you kind of accelerate your processes, but the big benefit is also then you're reducing the number of errors and the engineering changes that happen as you move into the manufacturing line. And we see customers that are seeing 90% reduction in their engineering change orders as they move into production, because they've been able to automate and identify a lot of these errors much earlier in the process. And that's giving them real value as they move through, make a seamless transition from engineering into manufacturing. And so last but not least, about the design aspects of engineering, because you now have this, you're operating in this digital world and you have this digital twin. It really starts to enable the virtual reality piece. To be able to provide this fully immersive 3D environment with higher-end renderings, and I always think about it, being able to design in context with virtual reality. I think about my own personal experiences where we would design parts when I was a younger engineer, and we'd look at them on drawings, we'd look at them on CAD tubes all day long, and it was always kind of fun to listen to some of the engineers when we'd walked out on the shop floor, and they'd say, "Wow, I didn't expect it to be that big." or actually some, maybe worse, they didn't expect the access hole to be that small for the mechanics that had to work on it. So, because they didn't really have that they couldn't visualize in relation to the part, made it a little bit harder. So now I think we're starting to see where you can start to be really designing in context. You're starting to see it from the viewpoint of the technician or of the maintenance technicians. So you're able to look at a lot of different design alternatives, especially as more and more people are working remotely, to be able to collaborate on virtual design reviews and maybe accelerate that. I think at some point in time, companies are going to start looking at, can they eliminate some of these gated design reviews? It takes a lot of effort to set up for a design review. You're doing PDR or CDR. And if everybody's kind of working more in this, continuous virtual environment, maybe you start to eliminate some of these design reviews, and certainly really reduces the need for mock-ups. And so it does change how engineers, kind of view the world now. And so it's an interesting change as we go forward, and an interesting technology, I think, as we go forward. And, I guess I would characterize it, to me, it feels like it's, changing the interface of, how the engineer interacts with the design. But it's enabled by the fact that you have this strong, powerful digital twin, and that you're able to leverage that and apply new interfaces. So I'm going to move on to the manufacturing. I have a handful of slides left here. So, but how do you accelerate your production rate? Your production ramp ups as you're moving. Your product enters into service. You deliver a handful the first year, and then you want to deliver 20 the next year, and then 80 the next year. And you think about some of the production rates these companies are looking to get. How do you accelerate those production rate ramp ups while still meeting your quality targets and delivering your products faster? As we talk about intelligent manufacturing, we really want to help. It's about increasing this production rate ramp up using closed loop manufacturing systems. And so having the seamless transition of from engineering to manufacturing, that really providing an end-to-end digital thread for the whole process. We also talk a lot about shifting left. So, how do you do more virtual manufacturing so that you're getting more information as part of your concurrent engineering processes, and you're being able to feed that information to your design teams. So you start to have an opportunity to concurrently mature your manufacturing and your design processes. And then finally, virtual commissioning, the ability to really simulate your processes and your tooling and your planning before you start committing to cutting metal. So and so I mentioned, I talked about Boeing and their T7 earlier. Another one that's an interesting story is the paradigm shift that we're getting with digital manufacturing. And this article was in I forget, I think this might have been Aviation Week as well. I should have put that notation on there, but it was in August, and it was an article about the UK's Tempest program. So it's the UK's next sixth generation fighter program. It's BAE with Rolls-Royce, Leonardo. I think Saab is involved with that now. There's starting to see a lot of companies lining up on this, and it's a pretty fascinating program. And but they, as you go through the article, it's talking about the fact that they're really looking at a fully digitized factory, and their focus. I was on a panel interview with Andy Schofield, who's their director of manufacturing. I don't know, it was about in September, I think, towards the end of September, and he was talking about the fact that they're all of the work that they're doing, they're with the program. There's a natural tendency to assume that when you're developing a new program, that a lot of the technology is being focused on the engineering piece up front and the development of the new technology for the airplane. But in fact, they've taken a different approach on this one. They're really taking a hard look at how they're going to build the airplane, and how are they automating the processes, and how they're using robotics and additive manufacturing to really drive the cost out, because that's where the cost of the program is at. And so being able to build the products faster, to be able to build them more reliably with higher quality, and then they're going to use that information to drive into the design. And to me, it's just a bit of a paradigm shift. But think about that Boeing article, those references that I made earlier about the Boeing T7. A lot of the references that were in the article, when they talked about model-based engineering, they always talked about a manufacturing outcome. So they were always pointing it towards how is it going to help it make it easier to build. And here at BAE, they're doing the same thing. That's pretty, to me, I think it's part of that paradigm shift as companies are looking at the capability of the tools and solutions that are available to them that's occurring, that's helping them go faster. So what does that look like at different companies? So when we talk about a closed loop manufacturing system, you start, and when we talk about the digital thread and how you have this seamless transition from product design into production. So starting on the left with product design, as you move from your engineering into your production planning, you take the engineering bill of materials and that transforms into the manufacturing bill of materials. You're doing all your process planning. You're also looking at, the process validation, the simulation, the virtual commissioning that I mentioned earlier, and I'll show a quick video on that here. The line design and optimization, and your quality, and think about how you're designing it for quality and having that connectivity from engineering in these different realms around the bill of materials, the design for manufacturing, design for quality. You could probably, if we're talking about product support, you'd have down here on the bottom, you'd have design for product support. And you'd have a similar flow that looks like this. So anyway, moving that into your planning processes. And then as you move into your production execution processes, moving into your as-built, the routings that's required to actually, build your product, and the work instructions and the inspection plans. The real, this is the real production system. So all the planning material drives that directly. And then down at the bottom here, we have the insights from production, the continuous improvement. So earlier when I showed the twin and I talked about the difference between the production digital twin and the real production, and we had the feedback loop of the process optimization. This is where those data insights come. So as you're collecting the data on how your production processes are working and feeding that back into the twin, closing a loop back with your twin, you're able to optimize your processes, and you're able to improve your maintenance cycles for your factory because you have an understanding of how your machines are operating, and you have a better understanding when maybe the process is going out of control, and you can take proactive action. And so this is what we talk about a little bit with the closed loop manufacturing system, be able to show all the way back to your product design, how you're building, how the real production is operating with it and providing that feedback. So here's an example of the comprehensive digital twin and the key to virtual commissioning. And really it's having this understanding, as you're going through and you're assembling the process, you're able to see where you have clashes. It was moving a little bit quickly there, but you can actually see how the operators are going to interact with it. And I'll see if I can play that again. But so you bring the wing in, as you're bringing it across, you note that it interferes with one of the tools. And so then you have to figure out how you're going to move the platform around. And now you're able to manage and understand this dynamic clearance throughout the production processes. And so, this is a pretty key element as you're going through these plant simulations and actually understanding. You can set up your rate tooling. You can set up how your process, how your products are going to flow through the plant, and you really understand if there's a problem. And you think about some of the changes that are happening once you start building the parts and you realize that the tooling maybe doesn't work as you intended, or that you have an interference and you have to start making changes to either the part or the tooling. Again, it can result in significant downtimes. And so a lot of customers are starting to see this benefit. We have another fun example out there that we're working with Pearl Harbor, and they are they're doing when they bring the ships into dry dock and do a big maintenance cycle on them. It's like setting a factory up around it. They've got cranes, and they have all these back shops, and they're able to orchestrate the entire thing. They've digitized their entire process. So they've digitized their ships, and they've digitized their depots, and they're able to optimize all of their process flows. And the Navy has found significant reductions in time due to the ability to simulate how they're going to maintain their products. And so it's an interesting application of this technology as well. So we already talked a little bit about, we talked about the virtual commissioning. We also have the same thing with the automation, being able to, bring more manufacturing processes in, more automation, being able to leverage this advanced manufacturing technology, being able to simulate it. It's much more intelligent and connected. because you now have the data that's available with how the machines are operating, and they're feeding that back into your production digital twin. And it's much more flexible to changes and the ability to adapt to new processes and new products. Another outcome, much like on the engineering side, where you have virtual reality and what you can get, what you're actually able to achieve because you have the full up digital twin, really about bringing your 3D to the shop floor. And so we also have technology, where we use cameras to, help accurately locate parts based on the 3D models. And so instead of having paper out here on the system and having to rely on, some of the operator skill set, you're able to help automate some of those processes. So you can verify and confirm that the correct part's been installed. You're able to automate the checking of the installation to verify that it was installed properly, the right orientation. And then just as importantly, because you're moving away from some paper, you're able to automate the recording of the task completion. So by just quickly pressing a button, you're able to check that the part was installed correctly. And once you say, yes, it was, it's now automatically recorded, and you don't have, you have much less room for error on something that was inadvertently recorded. And similar to that, bringing the the augmented reality, even into the operators, maybe it's through, augmented reality is being incorporated in mobile devices or even wearables. We're also looking at, how do you tailor the work instructions? So if the operator is, you can tailor it to an operator. If it's a new operator, maybe you want to give them more instructions, more work steps. If she's done it 100 times, then you can give her fewer instructions. So the learning curve, you can start to account for the learning curve. And instead of giving, like the 50 steps you need, maybe you give the 3 steps that you need, and you can be much more proactive about it. And if something changes, if the design changes and you have to, kind of go through that learning curve again, you can tweak that. And so you start to optimize the work instructions really based on the operator, and you take advantage of the operator's capabilities and knowledge and skill set instead of just sending them the same thing over and over again. Again, with this, you're, with wearables, start to do the automatic part verification and, automate the recording of the completion of the tasks. And we're seeing this in both manufacturing and product support. And a lot of times they're the same processes, whether it's a work instructions to build a new product or to maintain a product, you have to be able to provide that to the technician in an effective way. And finally, some of the advanced manufacturing with the, additive manufacturing. And I think, to me, additive is, I think it's going to totally transform some of our manufacturing operations as it comes online. I mean, obviously there's still some regulatory hurdles that we have to address, getting, understanding the process, process controls and how the parts are designed, how the materials are produced. But it is going to change, how we're going to design and build parts. I look at some of these parts sometimes, I'm like, that are, generated, with additive in mind, using generative design. I'm like, well, I don't know how that would work. Well, my brain still thinks in terms of, 5-axis machining. And so I expect a part to look like what it would come off of a 5-axis machine. And when you unlock yourself and you start to look at those parts and you actually only put the material where it needs to be, you get a much different looking part. And you know what, it can be a lot lighter and much more efficient. So one of the things that we are seeing is simulation analysis tools can help aid in solving the regulatory challenges. We've been doing some work with the ability to understand how the materials are being processed as the parts are being produced, and using some machine learning to help speed up the development, the analysis of all the variables that occur as you produce parts. And so again, I think simulation and better analysis tools will really help additive be adopted more quickly. And then I think this also helps pave the way to implementing new materials and manufacturing technology as you start to think about how you can print materials instead of producing them in bulk, and then working, machining them, cutting them, whatever we would normally do with subtractive manufacturing. So. But when you think about how a part goes through the process, this is really the true digital thread of a manufacturing process. You start with a part that's designed. In this case, you have this is what the part looked like in my mind when it was going to be built on a 5-axis machine. But as you go through topology optimization and the generative design, you get a much different looking part. And you go through lightweighting so you can take some of the material out. So instead of being constrained by just the capabilities of the machine, of the milling machine, you're now be able to put the material exactly where you need it to have. You go through a validation of the part, using process simulation. After you print the part, you do a little bit of post-processing and you get your final part. But the benefit here is you have full connectivity. You have a full digital thread throughout the entire process. It's not a disconnected process. It's a fully connected process with a good digital thread. And then I like to have some fun with this. I think about this on the left. If, metallic structures, 1960s, 1970s, you're building a horizontal tail. It's got 200 parts in it. It's a bunch of sheet metal parts with some machine parts. And it's it was very labor intensive. It required a lot of tooling. And it required a lot of machined parts, or a lot of just hundreds of parts, and then in the 70s, 80s, actually I guess it would be more like the 90s, you started to see composite structures being more adopted. Companies started moving to co-bonded and co-cured structures. You got rid of a lot of parts. Maybe you had 10 parts now, but the tooling was still pretty complex and still pretty expensive, and the labor hours are still there. And now as we start to think about additive, you think about printing that horizontal structure with additive now, and you get rid of all the fasteners, maybe. You get rid of a lot of the tooling, definitely. And you get rid of a lot of the labor hours, which also can be beneficial. And the cost starts to become very attractive. And so it changes, it will change how you design and build parts. It will also change the capital investments that a lot of these companies have to make. And they're buying machines now, printing machines that are very flexible, can produce any number of parts versus building dedicated tooling. And so I think it's going to be kind of fun to watch to see what companies are able to do with this technology as they get more and more comfortable with it. So I'm excited about that as part of the future. All right, so I've just, as I wrap up here, we talked a lot about a lot of subjects today. We talked about the digital twin, the digital thread, and I tried to provide some examples around simulation, electrical system design, and how we're tying it together with model-based systems engineering, and then how that flows into manufacturing. And obviously it also then flows into product support. But, just kind of, to step back and think about, we started talking about innovation, and we started talking about, how do you get, in this world that's getting much more complex with urban air mobility and supersonic aircraft and new requirements for defense and space. And I didn't even go into space tourism and who's going to build the first hotel in space or anything like that. But it's how do you get there faster, and how do you get there with competitive advantage? And again, companies that with the using the most robust digital twin, and having that rich understanding of their products, they're going to be able to design new products faster, and they're going to be able to optimize their production processes as well as how they're supporting their products, and using out of the box, more configurable solutions, but with personalizations available that you can be implemented quickly. And then finally being able to really utilize a good open ecosystem, that you can bring these new technologies online faster, that you can integrate with any of any current solutions that are out there as well. So the open technology really helps. The open ecosystem really enables a lot of companies to, help manage their changeover and help manage their digital transformation and be able to do it much more efficiently. So, so those are really, again, the keys to competitive advantage using digital transformation. And so with that, we'll just say, look forward to your questions now, and what questions you might have. Thank you for your time. I really appreciate you being here today and hosting me, and just say thank you, I guess. So, all right. So, and what questions do you have?
Yeah, thank you. This is a really great talk. So folks, if you have any question, you're welcome to type in Q&A or raise your hand to be unmuted. So say, for example, Gus, if you want to ask some more question, you are unmuted. Yeah, I do have a quick question while waiting for others. And so you mentioned about the Boeing T7.
Yeah.
So do you think that your solution will be helpful for Boeing Starliner and 737 Max, to help them to, see the issues in,
Yeah, no, it's I I think, well, I think the simple answer is yes. I think, they're already using a lot of digital solutions, and I think as they start, you know, Boeing, was one of the leaders in um, digital transformation. I think if you go back to um, back even like the 777, when they were first designing that, they were developing very innovative manufacturing techniques, using model-based engineering, model-based design. So, Boeing, I think, has been one of the leaders in terms of, digital transformation for a number of years, which makes it easy to kind of highlight them. I mean, I was aware of what they were going on, when I worked at Learjet, and so in Wichita, Kansas, and so absolutely, I think, these tools can help any company as they work on new products, new solutions.
yeah, you can see there's a question in the Q&A.
Yeah, it's I would say that it's still a bit of a mix. I think some of the customers are, so the question is, do most companies end up customizing their software integration environments or use them out of the box? I think companies, there's been a tendency, there's been heavy customizations for the last, um, you know, you know, for a long time. And so customers still have a lot of these legacy processes in place. And so we're seeing more and more of a mix. I think, as we move into more of the greenfield, situations with some of the newer companies, they're not fighting a legacy system. That they tend to use a lot of products out of the box. Some of our larger customers that are farther down the digital transformation path are now trying more and more to move out of the box. So I don't know. I don't know really what percentage I would put on that, but the greenfield situation, certainly there's a lot of out of the box. The brownfield situations tend to use a little bit of a mix of customizations, but they're trying to get to out of the box more and more.
Okay, so how about this? Because you talk about like electrical design and the manufacturing, and we have a talk a few years ago about the Air France 447, the tragedy during the storm lightnings. So do you think if they have implemented your solution, in which way that, because there, if I recall properly, there's also some issue about the operating systems, feeder tubes, those kind of
Yeah.
things, and would adapting this your solution might foresee those issues even from operating systems or those kind of things, sensors.
Yeah, I think that I, so I should caveat the answer as I don't know exactly. I forget what the exact failure mode was there, and if they, as I trace back in time, what actually caused it. As far as if I don't recall if it was a design issue or what the specifics of that were, but I think stepping back and thinking about being able to model the sheer volume, manage the sheer volume of things that you have to look at. With the system modeling tools now that are out there, the system safety tools, and being able to understand the data flows. I think the tools today are more, I will say, a little bit more. They're stronger. They make it easier to analyze more data, and I'm sorry, maybe more scenarios, to look at more scenarios faster. And you might have had an opportunity to find that. I can't say for sure. My sense is that there probably is. Yes, I think that there's more tools out there to help find those problems. I mean, when we start talking about some of these generative, design and using simulation for all of that design and analysis, we start talking about looking at hundreds of thousands of scenarios, and that's that we couldn't have done it in the past. And I think so. Yeah, it's quite likely that you'll be able to look at more of that and maybe identify more of those challenges faster and earlier in the design process.
Also, a quick question. You mentioned the digital twin. Is that actually a specific product name of your product, or just a terminology?
Yeah, it's more of a terminology. I think in full disclosure, I think I think digital twin is becoming a pretty common word in the industry. There's a lot of customers. I'm sorry, a lot of our a lot of the suppliers or solution companies like ourselves use digital twin as nomenclature. There's everyone has a little bit of a different I'll say take on what the digital twin is, but or maybe have a little different definition of the digital twin. But the fundamental definition I think everyone generally agrees on is it's the virtual representation of the physical product and how it's represented. And so different companies provide different elements of the twin. So I would say it's a pretty common knowledge. I'm sorry, it's a pretty common nomenclature, and it's general agreement on that terminology.
Yeah, there are two questions there, but just a quick, can your system solutions integrate external software like ANSYS or some other things?
Absolutely, we do today. So speaking specifically about Siemens software, we do integrate with pretty much any of the tools. We try to integrate with all the tools out there, and we can, and we don't. Usually if there's a tool if there's another solution that we haven't integrated with, it's because nobody's ever asked us to. It's usually not a technical issue. So, and a lot of those tools, so like a lot of the Siemens solutions are their foundation is parasolids. So the kernel is called parasolids, and that kernel is used by a lot of the other tools out there. So, such as like, I know ANSYS uses parasolids as part of their kernel as well. So that actually makes it easier for the two systems to talk. And that's actually what makes it easier to move those down into a lot of the manufacturing solutions, because they're built on the same kernel. So I see a couple of questions out there, and I know we're just a few minutes out of time. You want me to try to take those two questions real quick, or?
Yeah, you have roughly like 3 minutes.
Yeah, so let's see, my organization, Maker Squad, recently launched a guest speaker program. Do you have any advice on how best to recruit speakers from the digital manufacturing ecosystems? Yeah, I think, generally speaking, when you reach out to a lot of these companies directly, there's a large, there's the large companies, SpaceX, Northrop Grumman, all these companies are doing it. Usually, I guess when we reach out, we just kind of, we try to find somebody and we reach out to them directly. If we don't already have or we try to leverage an existing relationship. Certainly, working through an organization like AIAA can also help with that. And I know that, we get contacted a lot by companies or by organizations that are looking for speakers too. So, so that's, I don't know if that really answers your question. I guess I don't have great advice on that. And then the last one, does the environment require more thought with regard to protection of proprietary information, protection from adversaries, competitors, creating a digital evil twin? Absolutely. So, we do have, part of our system and part of a lot of the systems do have intellectual property protections on them. There also is more and more, I should say more and more consideration around cybersecurity, especially as you're starting to see more, like the self-driving cars, the autonomous vehicles, and also all the drones, the autonomous, like the, air cargo type drones. There is a lot more work being done in the area of cybersecurity to help protect those, and to build that into your software so that people aren't able to basically hack in and either hack in and steal your data, or to hack in and do something adverse to your system. So yeah, there's a lot of emphasis on cybersecurity now. So all right, and I think we're kind of at the time there. So
that's great. Yeah, that's also my question about the cybersecurity. That's because you mentioned the Russian, they're doing all things. Yeah. Okay, that's great. Yeah, this is really fantastic. So really appreciate. Stay in touch. We'll try to have you back anytime you like.
Yeah, I'd be happy to.
Yeah, this is so exciting. Very important.
Excellent.
People love
All
it.
right.
Thank you so much, Dale.
Thank you very much.
Appreciate
I hope you all have a great day. Thanks.
You too. Thank you. Thank you.
Goodbye.
Okay, so we'll be moving to the next presentation. So we are